All right, so I just realized that consistency is such a hard topic in general, and you have the feeling that it's going nowhere, that I do want to point out big things, but I don't want to go through the tediousness of all the consistency models, at least data-centric consistency, okay? So I just want you to remember, sequential consistency means you're equivalent to some kind of a sequential schedule. Now, it's important to know why that's interesting to have, but it's very hard to prove that any schedule, in fact, has that property. Knowing that the problem is there, or that the property is desirable, doesn't necessarily point out to any solution. I mean, you cannot just dream up a solution for sequential consistency. You really have to go and read hard research literature to see who found the solution, okay? Also, this kind of consistency ends up being very problematic from a performance point of view, okay? But it's important to know sequential consistency, right? Means you're equivalent to a serial schedule. Okay, not going to go through details because I don't think they matter that much. If you want, you can go over these slides and see the tic-tac. But again, okay, this is consistent, this is not consistent, so what? It's important to know that solutions exist, and databases did solve completely this kind of problems, the sequential consistency problem. Okay. The other big idea we had was causal consistency, right? You don't insist that you're equivalent to a sequential schedule. You're only worried about what things could cause another thing. The differences are very subtle. You get a little bit more lag room, okay? Not that much, though. A different kind of consistency not mentioned at all. I mean, so consistency is consistency, but I have not yet pointed out the solutions. A lot of the solutions, either for sequential consistency or causal consistency, are based on locks, right? Locking operations can be performed both locally and globally. Right? How do we do global locking? Well, we talked about this. It's the mutual exclusion region. Remember all of that dancing that was happening with many messages going around in which you either asked the central server to say, hey, I want to lock, and they gave you the OK, or you had some kind of negotiation going on in which you try to grab, for example, half the tokens. You have to do that every time you're trying to acquire a lock. It's madness, right? You cannot go and do this kind of algorithms, right? So having a strict enforcement of these properties, especially when the data resides on multiple sites that have to be kept in sync, starts to be very, very problematic. This is why you have to consider different kind of solutions, right? One of them is this idea of grouping operations, right? There are many versions of these grouping operations. You're trying to get more stuff done. For example, once you acquire a lock, you might want to get more stuff done, right? Now, one of the reasons I'm not insisting on any of these things is the new trends are going exactly the opposite of this, right? Eventual consistency and forms of client-based consistency tend to be more important nowadays, and you're much more likely to bump into. So I want to spend more time on those, okay? Remember, we are talking about data consistency, right? Data-driven consistency. That's more in the realm of big servers that are trying to serve clients, and they have to be highly consistent with each other. That's happening when you're talking about financial data, right? If I do a financial transaction here, I would like that financial transaction to be consistent and be replicated reasonably fast to another site, at least to provide the right image in another site, right? So why is this important for money? Because otherwise, people are going to find ways to exploit it, right? So imagine, for example, that you don't have a particularly good form of consistency, and you're not propagating changes when it comes to money particularly fast. The system then can be exploited by various kind of people and abused to essentially make money, right? So if the changes are not propagated that you took money from your account, you can go at another site that your bank has in another country and get more money from there, more money from there, more money from there, right? The bank finishes the transactions. In the end, they figure out that you pulled out 10 times the money you had in the first place. Go and chase the money down. It could be a complete disaster, right? There is a clear decision made there, safety versus performance. So they really say, hey, I mean, you might want, for example, to do some kind of risk mitigation. You say, hey, if you're moving $10 around, I don't care. But if the amount of money goes over a certain amount, then I'm going to kick a heavier mechanism and try to get a stricter kind of consistency around. It's similar to some extent to, for example, what Amazon is trying to do, right? In which they say, you know what, we are going to pay the price rather than enforce an overly strict consistency model. So you can do a dial-in kind of performance versus consistency by essentially enforcing a different consistency model for a different kind of transactional operation you're trying to do. These things are very tricky, and I don't believe the distributed systems community does a particularly good job at tackling them or even has a big influence on these things because they are really dominated by the database community and large relational databases. So I'm going to have a completely different discussion in the database class about this. For this class, I want to focus more on client-centric consistency and the notion of eventual consistency because it's more in line with what people do with distributed systems. Okay, so let's switch to that. That's all I want to say about this data-centric consistency. I really need to go into complicated theoretical models and whatnot to properly describe it, which I don't think is valuable in this class. Okay, so let's see what the idea is in eventual consistency and how can you base consistency on the client's perception of things, right? So it's all about, in the end, what the client sees, right? So how many people here have seen any of the Matrix movies? Okay, so why am I talking about the Matrix? Well, I'm talking about completely fooling somebody. It's like virtual reality, right? If I completely fool you, you can't tell the difference, right? So this is very much related to that in the sense that as long as what the user sees, right, is consistent in a certain sense, it doesn't really matter what's happening with the data behind the scenes. Right? Now, when it comes to financial, for example, financial transactions, the things are very, very different because, in fact, I'm moving any of my transactions. For example, if I buy something using a credit card, it involves already two parties, and I need a notion of consistency that involves both parties, and things can get very complicated. But a lot of the problems when it comes to the user might, in fact, involve only the user itself. And it's more an issue of make sure that what the user sees is consistent even if the user moves around. So let's see what could happen if this doesn't work, right? So portable computers, for example, are somewhat problematic. In the good old days, people had access to exactly one computer, and that was problematic in itself, and it never really moved. We had enough IP addresses. Almost everybody had their own IP address. That was great. It was almost unheard of to say people move from one part of the internet to the other, and most of the time they access the internet only through, let's say, work, right? In those kind of circumstances, you said, hey, let's have a server in the department or server in the university, and you always go to that server, and that's the end of it. Consistency was relatively easy to enforce. The client connected it precisely to one server, and that server always provided a consistent view because it was trivial to provide a consistent view, okay? So, namely, think, for example, email server. I always contacted my email server. It was always the same machine, the same server. If somebody sent me an email, I could see it. If I send an email, I knew that I sent the email, and that was the end of it, right? Or more subtle things. If I read an email, the server knew I read an email and sent me all those special messages saying, yes, the message has been opened or has not been opened. Or if I deleted it, I knew that I deleted it, okay? Now, things can become a lot more problematic in the presence of portable devices, right? And also in the presence of, which is not quite discussed in the textbook, of this very aggressive caching that goes on all over the place and so on, right? And then suddenly you're extremely worried about consistency, even for something like email, when you keep on moving from one part of the internet to another part of the internet, right? So classic example, I'm sure you do yourself, is you have a completely different ISP at home and at UF. Not to mention that your phone, it's really, whenever it sees a network it knows about, it just connects to it and starts doing things. So getting inconsistency, it's a really potentially big problem, right? Because, I mean, literally, I don't even have to do anything. My phone just beep, 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 and says, yeah, I do emails and I do things and so on. So think that you are now Google. You're providing email service for an enormous number of people. You can't do this with a single server. You already know it. You have to design the distributed system, right, that is going to power this email, right? And one of the main issues that you have is exactly this. In particular, if somebody connects on one part of the internet, hey, they drive for 15 minutes and they can get in a completely different part of the internet afterwards, right? So in particular, for example, the home ISP that I have, I almost said Comcast, but it's Cox, right? Cox, might connect to the internet in a very different place than UF does. And by the way, that's almost guaranteed. Now, it turns out that Cox, locally in Gainesville, right, they have a special wire that goes from the local Cox connect to the UF because so many people connect in between. So there is kind of a shortcut, but hey, you take a plane ride and you go in an airport, you're going to be completely different part of the internet, right? Almost guaranteed, from the point of view of the architecture that Google has in terms of servers, that you're going to connect with another server anyway, right? Because that's how Google is running the business. They have so many clients connecting to this. So then this becomes a real problem. In particular, if I've done a certain operation here and I move to another part of the internet, I expect a certain kind of view of the world when I go there. So one of the particularly annoying things would be the following. If I, for example, delete an email here, and I go here and the email is not deleted, for example, that would be annoying. Right? So that's essentially some sort of a write operation. You're doing some writes, right? So in this kind of circumstances, especially when you could contact a completely different server just a few minutes later or hours later or whatever, you have to ask the question, what would be nice from the point of view of particular applications to guarantee in terms of consistency? Now, these are not going to be as strong a consistency model as the data-centric ones, in which you're guaranteeing things go in a certain order and so on, right? But nevertheless are important from users' point of view. Now, it turns out that, almost as it always happens, researchers like to put names on things, right? So to nail down specific kind of properties for these consistency models and give them some names, right? Now, let me give you, well, it's kind of a warning and a heads up on how things go, right? So I'm going to talk about 4 specific consistency models for the client-centric that are in the textbook. Now, the interesting question is, people at Google that designed this, did they think about these consistency models or not? Or do they even ever bother to say which consistency model are they enforcing? Now, I would claim that not. Okay? And that, of course, begs the question, why am I bothering to tell you about these 4 consistency models? What I want to give you, right, is the spectrum of things to consider. And even if you consider those things, if you want, instinctively, right, it's still better because you're aware of what to pay attention to, what not to pay attention to. The big problem comes when you're saying, yeah, whatever, it's going to work out, and things are not working out, right? So almost surely, the people at Google that had to code up Gmail did not really think too much in terms of a very strict way, right, a very theoretical way, but they thought instinctively about things like, oh, yeah, but what happens when you do this, and what happens when you do this, and we have to find solutions for these things, okay? So let's put some names on things, and let's see how, at least, we could formalize a little bit this stuff, even if we don't want to write heavy theory on this, okay? But you understand the issue. The issue is you move in another part, you contact another server, the view looks different. That could actually produce things that humans don't particularly like. People don't like inconsistencies. Now, people might tolerate certain kinds of inconsistencies, okay? So for example, I'm sure you do this. I read a particular email at home, and then I switch the device. And by the way, so this goes across devices as well. So it's much worse, right? You don't only expect consistency when it comes to servers. You expect consistency when you change clients as well. Because we are not, I mean, I'm using at least 3 of them, right? The phone, the iPad, and a laptop or 2 laptops or whatever, right? You would expect things to be consistent across the board. So certain things you're going to tolerate, and it's more than acceptable to tolerate. For example, when it comes to an email application, namely, I read an email, let's say, on the iPad. I move to the phone doesn't yet know about it. Oh, no problem. I'm going to drag the thing down. I know it didn't refresh. So change propagation, right? So this is what the eventual consistency is all about, right? Change propagation, an item changed and my device doesn't yet see it, you could tolerate that. Depends on how big the delay is. Or if you have a way to say refresh, for example, right? Other changes might be much more annoying, right? So maybe we're going to hit on some more examples later. Okay. So let's see these consistency models, right? So the first one, but again, so this is researchers putting names on things. Now, names are always very tricky. I mean, first of all, in computer science, you probably noticed. We take words, we deform them, and we call them technical terms. And we just throw them in for good measure, and then we don't even enforce any consistency in how we talk about them necessarily, right? So this kind of names are just that, names, I want you to keep that in mind. So don't expect if you go and bump into some guy at Google, if you mention monotonic reads, which I'm going to talk about now, that they are going to instantly know about this. Because the name made it into some papers, made it into some textbooks, didn't make it into another one. It might have a completely different name because another guy did a version of it and put another name on top of it, right? So it's not so much the name that's important. It's the idea behind it. What does it do? Okay. All right, so we're going to have these somewhat complicated things and see some examples, and let's see if we can kind of untangle them, right? So we say a data store provides monotonic reads, consistency, if, and these are the conditions, right? So by the way, monotonic refers to something that only goes up. This is a notion from mathematics. Now let's see what could possibly go up here. That means you don't, so remember the causality violations we were worried about before, right? This is the idea behind Lamport clocks, right? If something caused another event, I don't want to see the clock reversed for that situation. So the monotonic reads are roughly the same idea, but with respect to changes to objects, right? So if I read a value, right, if I make an operation on x, I don't want, when I read it again, to see an old value. I want to see the same value or a newer value, right? So it's OK to see. So if, for example, if I read, so well, email is not a good idea because it changes. But for example, for a bank account, that will apply, right? So if I look at my bank account from different places because I have different devices, okay, I do want to see either the same transactions that have happened if I looked at something like the last transactions, or newer transactions that happen. But I don't want to see the situation that was yesterday. Okay? Now, again, this is not about what you want in a specific circumstance or not. It's about putting names on things you might or might not want and formalize them. So the monotonic reads insists that any successive operation on x always returns the same value or a more recent value. Again, it's a choice. You want monotonic reads or you don't want monotonic reads. So when it comes to the framework designers, they have to decide, essentially, which of these consistency models they want to implement. When it comes to the application designer, you have to decide which one is important for your application, and then go and pick the framework that guarantees that thing. Okay? So it's this kind of consistency models are like contracts, right? So the framework designer says, I guarantee you that this is true. The application designer picks among these guarantees which one best fits the application. It's a complicated game, right? Because, again, ultimately, we could all run transactions, distributed transactions, and really have a very strong consistency model, but that will incur a very big performance penalty. So rather than doing that, we are going to try to negotiate on a finer note by implementing only limited consistency models. And then, as an application designer, you have to decide which one you go. By the way, you're going to do this quite a lot, right, when it comes to applications. I mean, either you or your boss is going to do this. Namely, select the framework to use for a specific application, right? And it can make all the difference in the world. So, for example, if you really want to do your own email service, you have to be very careful what are, if you want, the libraries and the building blocks you're going to use. Because if you have to build everything from scratch, it's really tedious, right? So knowing about these consistency models, and especially if you know what the library implements, even if it has a slightly different name, might make all the difference in the world for picking the right library to build things on. Okay, good. So let's see how this could run amok. Okay. Now this picture is a little bit confusing, and I have to explain. Yeah, it's right. So let me explain first what things mean. So L1 and L2 are, think of them as different servers. This is the timeline, right? And things happen at both these sides, L1 and L2, namely successions of operations on the timeline. Who does the operations? Well, various things, right? This is not tied to a particular application, right? So as we've seen before, we have reads and writes on any specific item. The item now it's only x, and we have two versions of x, an x1 and an x2 version, okay? So these are servers. This is the timeline. The operations in bold are the operations a specific client sees. Now look what happened. The client was first on L1 and then for some reason moved on L2. You got switched to another server. Now, by the way, this can happen either because you moved to another part of the world, what I argued before, or simply because of the internals of, let's say, Google. So How do you know that you contact always the same server? You don't really. You can get passed around. There are so many mechanisms to move, to hijack TCP IP connections and get passed around. For example, you try to distribute nicely clients to servers in the back end, but for some reason you make a mistake and you simply crowd one of the servers. What are you going to do? Let people suffer and have really bad experience? Well, you might move them. It's called client migration. Okay? So I'm just talking about might. But even if you want to do that and you want to enforce these monotonic reads, essentially what has to happen, right, is what we said before. If you read a value, you're only going to read fresher values after that and never stale values. Okay? So in this case, that's actually happening, right? So at this time, so the sequence of actions on this side is you write x1, and then your client reads x1. On this other server, you write x1 followed by x2. x2 is newer, right? And then you switch to this at the later time you read x2. x2 is correct here. Why is it correct? Because it's a newer version of x1. Right? How do we know it's a newer version? Well, first the write on x happened and then the write on x happened. I'm sorry, the version x1 was written and the version x2 was written. In this circumstance, though, that condition is violated because this change did not get propagated. So, right? So x2 it's a completely different version. So you read you read one version here, but you read a completely different version here. Inconsistency. Right? Now it goes on. There are 3 more. Right? So we have monotonic writes. So remember the rule. The first rule with the monotonic reads was I read the value. I'm always, it doesn't matter what I do, I read same or newer version of x. Good. Monotonic writes, right, let's see. A write operation is completed before any successful write operation on x, but only with respect to the same process. So notice that we are playing a certain game here for the data-centric consistency. We were worried about multiple transactions that look at the same data, right, which essentially means multiple clients. Right? So if I pay money through, let's say, some credit card transaction, then my view and bank's view have to be consistent. Right? So there are 2 parties involved if you want 2 different clients, servers, or whatever you want to call them. But all of this is only from the point of view of a single process, which, as I mentioned before, it might not even be enough because I keep on changing devices, so it's a different process in the first place. But at least from the point of view of a different process or a little bit extended, right? So for this monotonic write, a write is completed before any other write goes through. Right? So I write here. So remember, what the client sees is the bold part. Here, let me point this out. Somebody else was doing the writes. My client was just doing the reads. And I wanted the consistency to be enforced with respect to the reads the client sees when it switches from one machine to another. Right? For the writes, right? On this side, I write value x1. Right? And on this side, later, I want to write a new version, value x2. It has to be the case that value x1 was propagated to this other machine in order to provide this monotonic write consistency, which means you do the writes in the same order on different machines. That essentially means that I should not be allowed to write x2 until the version x1 was written on the same machine. Right? And that's really violated here. Right? So if I write x1 here, the change did not get propagated to this machine. I switch over and I write version x2. I'm violating the monotonic writes. Now, again, keep in mind that I'm not saying all of these things have to be enforced. What I'm saying is for every application, you have to decide if that's an important property or not, and then to ask the question, this specific framework does or does not provide that kind of facility. Right? So for example, when it comes to particular applications, this might be irrelevant. It's like, OK, fine, I don't care. I still have a version of X, and that's fine. Right? But for other applications, that might not be the case. It also depends on what writes mean. Right? So for example, if the writes are trying to be very clever and are just incremental writes, and that happens all the time in order to increase performance. For example, you might do things like this with distributed file systems like Dropbox, right? In which case you're really not, so imagine that you have a really large file, right? You're trying to propagate only the delta changes. if the writes are delta changes, it's crucial that you do them in the same order on all the sites, because otherwise you're going to get mingled stuff potentially, especially if you have slightly conflicting writes, right? So from the client's point of view, it's perfectly fine to have conflicting writes, because if you do them in a certain order, because the application can maintain the consistency, right? So when you edit stuff, things keep on changing all the time, right? So yeah, I made a change, but then I went back and I reversed the change without propagating the write, and then make another change and propagate it. It's fine, right, from the point of view of certain applications. If you don't push the writes in the same order, and this is what the monotonic writes is talking about, then essentially when you write x2 here, this will have an inconsistent view, right? Because the write 1 and the write 2 could have conflicted with each other. So those are the kind of circumstances when you might care about things like monotonic writes, when maintaining the order of the writes is very important. Right, in the first one, let's think about a scenario that works well for this. Right, so this is the bad example. Well, I mean, almost the same scenario works here. Right, you read one version or a fresher version. If this write, x1, would not have been propagated, again, the order of the writes might have mattered, and you're going to read inconsistent values. So maybe what you want is both monotonic reads and monotonic writes for incremental update situations. OK. Another one is read your writes. Right? So that means what? So if you're doing an operation on data item X, you always, so if you write, you always read your value, the value that you wrote, OK, by the same process. Now, this kind of consistency could conflict with the other ones. Right? So basically, so read your writes refers to, if I go, it's what I said about email. I go and I delete an item. Or I go, even worse, I go and I send an email. You see, deleting email, OK, I have some garbage that I didn't want to have. But think about sending, right? I send an email. The write operation is going to be mark in the section of sent emails that I send the email. If that is not propagated when I look again at my inbox, then I might not realize that I send the email again, which could make me look like a fool. I still have my father sending me duplicates of all the emails, just so to make sure I get it. OK, fine. All right? So read your writes might be desirable for certain applications. And this is really something that humans don't particularly like to tolerate when they don't see that happening. Now, in certain circumstances, for example, with the email, you can get away without promising this by allowing people to do that refresh. Right? And then, well, but even then, you see, that begs the question, why are you not refreshing anyway, just in case that happened, because it's so annoying. Right? So I look at my email, I don't see something, I know something is wrong, and I say, let's do a refresh before I start complaining about anything, because probably this did not get enforced, this read my own writes. Changes that I made on another client, on another machine, did not get propagated. Okay? So this is a situation when they do. Right? Again, this could be more complicated because other clients are involved. So I write x1. This machine got both the writing of the x1 and somebody made another change. And that's fine, because that's going to be a newer version. When I read this version, I'm going to get a consistent view, because I read something that propagated my change plus extra changes, which is OK. For example, I send an email, and then some other email got sent, but I still see my old send email. The circumstance does not have that. Right? So I write something here. The write doesn't get propagated to the other website. I read the value. And in fact, I'm not reading the change that I made. The change that I made does not get reflected. Now, these pictures tend to look a little bit almost the same. Almost the same circumstance could actually violate the consistency, multiple consistency models. And that's fine. Right? What it's not clear at all is the fact that you might not be able to enforce all of these consistency models. I mean, maybe it's desirable to actually enforce all of them. It looks like almost that The same solution might solve multiple such problems. Nevertheless, you want to have different names for these things, right? I keep on pointing this out, right? So we already have 3 of them, right? Still have time. So we had the monotonic reads. If you do successive reads, you always read same value or a fresher value. Monotonic writes, which means my writes go in the same order on all the sides. This one is read your writes. If I wrote something, I want to see my change reflected when I move on another machine. Okay. Writes follows reads. Okay, so let's see what this is all about. Right? So when you're doing a write operation on a data item that follows a previous read, it guarantees to take place on the same or more recent value of x that was read. Right? So this is about, again, about interleaving these reads and writes and what's acceptable. Let's see. Right? So I write an item. Then from my client's point of view, I mean, somebody writes the item. My client's point of view, I read the item. And then I write the item. The idea behind these consistency models, writes follow reads, is that I'm writing on top of the correct version of x1. Again, this is about consistency, right? So if both the writing of the version x1 and the writing of version of x2 actually happened, then this is going to be consistent because the write x1 got propagated. In this circumstance, and again, it's almost the same picture we've seen before. In these circumstances, this is a violation. But now it's not about the read. It's about the write. Remember, we had the monotonic reads had the same picture here about read-read, but now a read-write. The write here is going to be inconsistent because this version never got written. Again, if you have monotonic writes, this could create problems. Right? So it turns out that especially these file systems that try to propagate only deltas and not full versions of the file, with clients that move from one machine to another, are highly problematic. Because all of these models actually need to be enforced. Right? So here's an interesting question. You work at, or a competitor of Dropbox. You have to take some hard decisions with respect to what is it that you're going to put into those programs so that people run all over the place. Which consistency model are you going to enforce, and how are you going to run the show? Now remember, people are going to put stuff there. They don't really stay and think how well their application fits the model. Right? So it's probably worth pointing this out. When it comes to this kind of a discussion, so what consistency model it's enforced by certain frameworks and what do we do and so on, that's all nice and dandy as long as the discussion stays at the level of the application designers, or the discussion goes between application designers and framework designers. Nobody outside this kind of a tight interconnect is going to care until something wrong happens. Right? For example, your boss is basically a guy high up in the hierarchy that doesn't even know what distributed systems are all about. He just knows he wants to be able to accommodate whatever number of clients. You can't go back and say, yeah, but that's perfectly fine with respect to the consistency model we picked. He doesn't care about consistency models. He only cares about, do I see weird things in my application, or I don't see weird things in my application, right? So this kind of talk and this kind of a discussion you can't have with normal people, which means you have to ask these very tough questions from the point of view of the kind of user I have. What's the appropriate model to enforce? Now, that could be driven by what's available, right? So I have these 5 choices of frameworks. They have these different properties for them. Which one do I pick to better suit the application I want? Or even things like, is it time to start designing my own framework because none of them enforces the right thing? For example, if you are Dropbox, you might seriously consider doing your own infrastructure just because you're going to get an advantage over competitors, right? But even when you're trying to do that, you have to remember, and this is not reinforced enough in the textbook, you have to remember that detecting errors and asking the end user doing a little bit more work when such an error happens might in fact be preferable to a very heavyweight mechanism otherwise, right? So for example, in the case of Dropbox, Dropbox is really not trying to be very strict about enforcing these things, right? Why? Because they figured out what maybe I should call the Amazon model. They figured out that they can detect when something nasty happened and simply throw the problem in user's lap and say, yeah, you fix it now, but as long as it happens rarely, it's acceptable, okay? So if you're not enforcing these models, and for example, this happened to me, and the trouble is, I mean, it doesn't speak well for Dropbox, really. They should enforce these things more, because you can get in a really weird situation, right? So if multiple people work on the same Dropbox account, and that's really almost encouraged by Dropbox, right? If you're a developer, you might go and edit 10 files. Somebody else edited their own 20 files or whatever happened. And then you try to propagate your changes, and then basically almost everything fails, right? Because it's exactly this kind of a situation. When I made incremental changes, they made incremental changes, and you don't have this situation, for example, when writes follow writes. My changes did not get propagated to their side, because Dropbox does not try to push it in all directions. Their changes did not propagate to mine, right? And then we have inconsistent changes to a file. What does Dropbox do? I'll mention in a second the fix that Dropbox has. What does Dropbox do? It says, I can't put these two together. I give you both versions. You go and fix it. Now, this is, for example, similar to tools, collaborative tools like SVN or Mercurial or Git, right? In which they keep track of all the changes as long as you do commits, but you can have these conflicts and they need to be resolved by hand. Now, quite often, if I change this part of the file and you change this part of the file, and the tool can tell that we work in different parts of a text file, you could, in fact, successfully merge the two versions and say, hey, yeah, no problem. I add more lines here, I add more lines here. If we work on lines that overlap, then that's almost always impossible. If we work on binary files, that's guaranteed to be impossible. Okay? So what's the interesting fix that Dropbox found? A notification system. Okay? So you basically say this creates a problem for me. Rather than trying to be very clever about how I propagate these changes, how I do this, and so on, what I'm going to do is essentially allow people to run a tool in the background that augments the whole service. So when somebody changes a file and a change is propagated, I'm going to put a notification beep on the screen saying a new version of this file has been created. And if I'm editing it, I have to start being aware, and I click some buttons to bring the version and so on. Right? So there are multiple ways to enforce some sort of consistency in the system. It's acceptable to even have something like notifications in which you let people be aware that changes are happening so that they don't do overly nasty things with their copy because problems are going to come down the road, or to refresh more often their changes. Right? Especially when you have projects with large number of developers, right? And which is mandatory, a distributed version of this versioning systems like SVN, Git, and so on, then things could get really nasty in terms of how such changes are propagated and mitigated, right? And almost always, instead of having a very, very strict model behind the scenes, you might want, in fact, to just have a conflict resolution solution that's decent, plus manual overrides in case things run amok. So this is a very weird counterpart to even this kind of consistency models. What you're saying is, instead of being very strict about the consistency model we enforce, we are going to provide the mechanisms for people to correct such errors. It's really the equivalent, and again, it's unfortunate that these textbook writers don't write about this. It's equivalent to the optimistic concurrency control, to the optimistic algorithms that I mentioned last time. Instead of insisting on being very strict and making sure that you always correctly run the transactions and you are equivalent to a serial schedule, you just go and run, but you have a validation stage in which you detect if something was bad, and if you did, you go back to the drawing board. This is essentially what's happening with these tools, right? You work under optimistic assumptions, then yeah, we are not going to have things that conflict. Try to merge, you detect conflicts, and you throw them back to the user in case a conflict happened. Now, that can be done with developers, by the way, and they are used to this kind of things. That could be really bad with normal users when they use Dropbox, depending on what is it that they do. Okay. Now, this merging of things can actually be extremely problematic, depending on the format of the file behind the scenes. So you can go anywhere from relatively easy to disastrously hard. So for example, a particularly nasty problem is binary formats used by some of the products, for example, Office, right, Microsoft Office. Now, if things are in XML, and you know it's XML, and then you could write a consistency resolution tool, right, that knows at least how not to produce bad XML. But if you really, it's a binary format, you don't even quite know what it is, or it's very complicated, this kind of merging between various versions could be really, 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 really bad, right? In those circumstances, it's not even clear if any solution except always propagate absolutely all the changes and don't let anybody change anything in the meantime, it's actually going to work, right? So let me not switch topics. We only have about 10 minutes left. Let's bring this part of a discussion to an end, because I want to spend time talking about replica and replica construction and propagation and whatnot in the next week. Okay, and fault tolerance, how do you actually mask faults and do things, right? So let's think about some other applications that could be interesting in this kind of a context with this client-centric models, right? So for example, other interesting applications are things like, for example, chat applications, right? In which, of course, if somebody says something, you have to propagate the changes to everybody else. For example, in a chat application, the order in which the chat items appear could actually have a very big influence on what people expect. Right? So a lot of the ideas that we've seen before when we talked, for example, about totally ordered multicast, right, might in fact be needed when it comes to even something as simple as a chat session, right? People tend not to be very systematic when they write things in a chat, and reversing posts. I mean, something that would be completely disastrous is posts by the same person get reversed when they get pushed to different clients. Semi-disastrous could be posts of people get reversed. So again, this is kind of an interesting consistency conundrum there, right? So if I see posts in a different order than you do, when I have my chat session, let's say with 10 participants or hundreds of participants, it could spell disaster depending on who's saying what, right? I'm sure you can start a war if you reverse some of these things, right? So you can go anywhere from I don't really care and I can do anything I want to we have to be very careful, right? Depending on the circumstances. So it's really, really important to think in terms of this kind of consistency, right? Another very problematic thing is, and this is why you really need to look for solutions that have even proofs related to them, is this collaborative editing. We talked about this a little bit before, right? Now, collaborative editing sounds great, but if things start to look messy on either of the clients, it can be extremely problematic, right? Especially when you're writing code. So you literally can create arbitrary amounts of work for you if you don't have a nice way to deal with the problem. So the issue is related to the fact that if you have edits and they don't correctly get merged and propagated to various clients, right, then in fact, you can change the code in subtle ways and then debug for a couple of weeks to find which 2 lines of code got reversed. You see, if 2 chat lines get reversed, yeah, whatever, maybe we'll get over it. If 2 lines of code get reversed, that could spell really subtle trouble, right? So it can actually be so problematic if it happens to you once, you might even refuse ever in your life to use any such collaborative writing tool. And this is why possibly conflict resolution solutions in which we work independently and we try to merge and we try to push changes might actually be more acceptable than this kind of collaborative code writing, right? Now, there is a circumstance when things tend to be a little bit less than problematic. For example, when you're editing, let's say, documents, right? As long as you're really not editing the same sentence, you could produce probably some sort of weird problem there, right? If you work on different paragraphs and you see where everybody is, I mean, I get very nervous if I see anybody's cursor when I do collaborative editing, if it's too close to mine, right? I start the chat session, I say, hey, back off, go to another paragraph, don't stay in my paragraph. Because you don't know, right? You press a key and they press another key and God knows what happens. It's as if somebody is typing next to you, right? So even if any model is enforced, it can still be bad for you, right? So let's suppose we have a perfectly consistent use and changes are propagated very fast. If I write a letter and you delete the letter, it's still bad for me. Even if we have the same view and even if it's correct editing, whatever that means, okay? So Now, because of the new trends going on in what people care about and so on, you're going to see more and more of these things. So it's quite likely that at least some of you will end up working on this kind of issues, right? Can we get a collaborative version of this, a collaborative version of that, because that's the new trend. And then that's where this kind of consistency models comes into play. Now, it's probably worth spending more time on that issue alone, because it cannot be done with just this kind of consistency models. There is a much nicer solution that, in fact, it's not talking about consistency. It talks from a completely different point of view. It's still a form of consistency. This idea called operational transformations. I do want to spend the lecture just on that. Right? I want to discuss a little bit high-level ideas. And the big different point of view somehow is the following. You have to express editing in terms of this successive writes, successive transformations, right? And what you care about is that at all the sites, the same sequence of operations are in fact propagated, right? And there is a very nice theoretical characterization that talks about the wide spectrum of things you could do, anywhere from a weaker model to a very strong model. And as it gets stronger, it's going to get harder and harder and harder to evolve. Now, all of these things go through. I know of only a centralized solution. All the clients have to connect to the same server. Some of these issues, in fact, talk about multiple servers. I mean, you see in today's lecture, this is really about I move from one server to another server. None of these problems exist otherwise, right? So I want you to remember this. As long as we all connect to the same actual server, these are non-issues. It's impossible if you're on a different part in the timeline for this to happen and this not to happen. Well, at least if your server is single-threaded. Multi-threaded servers could create more problems, right? So that's going to be an interesting question maybe to ask is, hey, if I really run in multiple threads and so on, how would I even enforce this kind of things? But when you run multi-threaded, you still have very fast interconnects between what the different threads do, right? Unless, again, you're trying to kind of push the limit, right? In the database class, for example, I do discuss about transactional database engines that push the limit to extremely, a lot in terms of how many transactions they run, but they do so by restricting what transactions you can run and simplifying, right? So if, for example, even in the case of transactions, right, if you could send different transactions to different places if they don't conflict, right, then that's a nice way to actually increase performance. If you know for sure there is no conflict, and you can actually determine that possibly from some sort of metadata about the transaction, right, then you know what to do. Now, there is another assumption here, and I want you to be aware of it, and that's going to end the discussion about the consistency. We assumed throughout these lectures, and I did not explicitly say this, that the client does whatever it wants, and we don't know in advance what the client needs to do. Okay? That's not necessarily the case in a lot of circumstances. So what I mean by that is, when you're doing a credit card processing, right, you know for sure what's going to happen. You're going to take money from one account and put it in another account, right? And you can even know which accounts are you talking about before you, in fact, fully run the transaction. So you can, in fact, under certain circumstances, if you have a full description of what the transaction is all about, so-called compiled transactions, you can, in fact, run analysis to determine if a conflict would happen. Or especially important is if you know for sure a conflict won't happen. So a possibility is the following. To, in fact, do some routing of these transactions before you run them and before you say I commit or I don't commit. You look at the transaction and say, you know what? I know for sure that that server can completely resolve the transaction and not ever produce a conflict. For example, you can create these regional servers, right, in which you say, you know what? You're trying to do a credit card transaction and with your bank, but you're in Gainesville. I'll send it to a Gainesville server, and that's the end of it. The moment you do that, as long as you don't overwhelm that Gainesville server, let's say, then you can safely run the transaction without significant conflicts, right? Because you can afford to apply the classic solutions because you're not going to have an enormous number of transactions going on, right? So this is a clear possibility, and you can bet, for example, that Visa or MasterCard use this kind of tricks in order to achieve very high throughput in the transactions. Now, what's very clear, though, is general solutions that are high performance don't exist. So you can't expect, throw at me any transaction you want, and we have a large number of clients connecting that has miraculously run it fast, right? So the more you know about the circumstances, the better off you are with specialized solutions that could run at a much, much higher performance than other things. And you have to consider all of these things, right? So you either relax promises you make, or you use things like precompiled transactions to know exactly what happens before you run it and to separate who runs on one thing. The interesting solutions that I discussed in the database class about those kind of high performance transactional systems, right? That's kind of all I wanted to say about consistency. I'm not going to pick up the topic anymore. We talk only about replication, and we talk about failure starting next time, which are important high-level issues. Okay, I will have a quiz over the weekend talking only about consistency. I'm going to have 4 questions about consistency. What's this and what's that and all that kind of stuff. Okay, and then we are done. We just mentioned high-level ideas about consistency.